Hello everybody. My name is Ruch Shah and my teammates are Vedansh Kumar and Sarthak Chaudhary. Together we have created a WGAN based framework for aerial image denoising under mixed noise conditions. We have done this project under the guidance of Dr. Geeta S. from the Vellore Institute of Technology, Chennai. Our subject name is Digital Image Processing, course code DCSE 403L of the winter semester 2024-25. Let's delve deeper into the problem statement we picked up. So we decided to do aerial image denoising, where aerial imagery is generally prone to having various noise types. Each image can have a fusion of random, multiplicative, Gaussian, and salt and pepper noises. Existing methods usually address only one noise type each, such as median filtering, frost filtering, BM3D filtering. We look to create a framework that can handle any types of noise in any mixed proportions and fusion, all in one framework. While working on our project, we looked at various papers, one titled Convolutional Blind Denoising of Real Photographs. It used a convolutional network CBD-net to denoise images. The model consisted of a noise estimator and a non-blind denoising subnetwork. CBD-net was trained on both real-world images and synthetically noise-generated images in clean noisy pairs. The key limitation of this model, however, was the performance degradation when applied to images with different noise characteristics, and also the heavy reliance on the accuracy of the noise detection layer. Another paper we looked at was for the model DNCNN. Here, the authors used a feed-forward deep architecture that integrated techniques like residual learning with batch normalization, accelerating the training convergence and improving the denoising quality. The model created by the authors was designed for blind denoising, thus handling variable noise levels without prior specifications. It worked by implicitly removing the latent clean image in the hidden layers. This allowed us to train a single DNCNN model to tackle several general image denoising tasks such as Gaussian denoising, single image super resolution, and JPEG image deblocking. I'll now pass the presentation on to my teammate Sarthak Chaudhary.
Hello, I'm Sarthak Chaudhary. I'll be taking on for the related works. So, similarly, we have taken another CNN-based model, FFDNet. It is a custom CNN model tailored for practical image denoising tasks. The FFDNet achieved this practicality as, unlike other models that required separate training for every noise intensity, FFDNet introduces a noise level map as a part of the input, enabling a single model to adapt to a continuous range of noise levels. This method enhances generalization for real-world scenarios where noise levels vary spatially across an image. Hence, the proposed model from the paper proved to be better than other conventional convolutional neural network-based models. Then in another one, the paper aimed to tackle problems of denoising real-world photographs with complex noise patterns using a single-stage blind denoising network known as RIDNet. The method employed a residual-on-residual design, which allowed for flow of low frequencies, helping in the network's ability to reconstruct the clean image alongside with a feature attention mechanism allowing the network to focus on the most informative features among the different channels. RIDNet achieved PSNR improvements of 9.5 decibels and 7.93 decibels over FFDNet and CBDNet, respectively. The effectiveness of the model, however, can diminish when applied to images with different noise characteristics as compared to the training. About the dataset. The dataset comprises of four different aerial datasets. First, UC MERS dataset. It contains 21 scene classes and 100 samples of size 256 into 256 in each class. The WHU RS19 dataset. It has 19 different classes with 50 samples of size 600 into 600 in each class. The RSSCN 7 dataset contained 7 scene classes and 400 samples of size 400 into 400 in each class. And finally, the AIDNet dataset has 30 different scene classes and about 200 to 400 samples of size 600 into 600 in each classes. The dataset was made using three different noises, and all of the three different noises they were introduced to the images randomly, and equal amount of each noises were then present in the dataset for each for images. So there were a total of 4,583 random Gaussian and multiplicative noises. The noises, as you can see in the presentation, are there. The random noise is unpredictable variations in pixel values, often caused by electronic interference or sensor imperfections. It does not follow a specific pattern and can affect any part of an image, leading to a grainy appearance and degradation in image quality. The Gaussian noise follows a normal distribution with most pixel errors centered around the mean. It is commonly caused by poor illumination or high temperature in image sensors. The noise adds to every pixel independently, resulting in a soft, grainy texture. And finally, the multiplicative noise is signal dependent and varies with image intensity. It distorts images by multiplying the original signal with a noise function, commonly occurring in radar or ultrasound images. The noise level increases with brightness, making the brighter regions more effective. So that's it for me. I'll be passing the video on to Vedant.
So hello everyone, I am Vedansh Kumar and I'll talk about the model architecture. So we have proposed a unit generator. The unit generator basically consists of two parts, which is an encoder and a decoder. What encoder does is that it downsamples the spatial resolution of the image and it extracts the hierarchical features from that image. How does it do that? It consists of one convolution block, the convolution blocks, and a match pooling layer. Now, what does a convolution block consist of? A convolution block will consist of a convolution layer, batch normalization, and ReLU layer. And now, similarly, on the decoder part, the the unit consists of basically a convolutional block only, which consists of convolution 2D, batch normalization, and ReLU layers. And it helps in upsampling. So how is this upsampling done? For upsampling, our transpose convolution takes part, which with the help of bilinear method, it helps in upsampling our images. And now what we are seeing here is that there is an encoder and decoder, but we see that the image is getting compressed and then then the spatial resolution is getting increased. So how do we think that the details of the image will be maintained? So in order to maintain these details, we have these skip connections here. These skip connections will help to provide the details which are the lower level spatial features which are not to be forgotten while doing this whole process. So these transfer it to the decoder and help in providing an output which have a structural similarity to the clean image. Now, as of for the discriminator, so now in a normal discriminator, what we see is a normal convolution block which will have a 2D convolution, batch normalization, and a leaky ReLU, and finally a convolution 2D layer along with a sigmoid layer. But what we see here is that our model won't be containing a sigmoid layer. Why is that? Because we are using Wasserstein distance instead of the probability. So what does Wasserstein distance tells us that it compares the distance between the real image, which is the cleaned image, and our denoised image, and then provides output which tells that this is this much fake or there is this much difference in the images. So in order to get a good image, we should have a good and proper loss function. So our loss function comprises of three parts, which are perceptual loss, pixel-wise loss, and generator loss. So now, perceptual loss. What does perceptual loss do? Perceptual loss is basically calculating the value with the help of a pre-trained model, like let's say VGG or ResNet or anything. What here we have used is a VGG19 model. This helps us to preserve the high frequency details. And as we can see, how we are going to calculate is by summation of all the pixel values with the summation of all the pixel values which we get from the processing of the clean image minus the processing done by the VGA19 of the denoised image. What pixel loss helps us is maintaining the pixel-wise difference between the clean image and the denoised image. So how will it help us? It will help us by maintaining the color pattern in the present in the image. Let's say if I have a green, I want the green to be the output in our denoised image. But this cannot be done by every loss function, so which here we are using L1 loss for that. So now I'm going to talk about our results. So we have used two metrics which are widely used by most of the people who are working in this, most of the people and researchers who are working in this field of denoising, which are PSNR and SSIM. PSNR is peak signal to noise ratio and SSIM structural similarity index. So SSIM means that how much is the structural difference between my image? Is the shape of the building in the clean image and my denoised image the same, or is it different? And for PSNR is so what my image will contain is a noise and a signal and the actual signal. So it will calculate the difference between them and give us a ratio with the maximum pixel value present. Now, upon calculating the metric score, our PSNR value was 33.04 dB, which is quite good for a denoiser, and for SSIM our value was 0.9172, which is also quite good, showing that the structural similarity is maintained between the clean and the denoised image. Here also I have given an example like this, which we can see. So 3, 2, 1. So as you can see, here is a clean image, here is a noisy image, and here is a denoised image. Now we can see that the noisy image has some kind of green, blue, white colors here, and which is reducing the quality of the image and makes it difficult for us to see the details present in the image. So our denoised image is quite a bit similar to our clean image, showing that their structural similarity is maintained and hence validating our metrics. So thank you guys for watching this summary of our whole research, and I hope you have a good day.